Alright, last piece here, we are going to talk about some of the significant patterns on the periodic table that we call periodic trends. So in order to understand what's happening and why the trends are the way they are, we're going to think about some of the ideas that we talked about before related to electrons and where they are relative to the nucleus. So there's this phenomenon that we call the shielding effect. And the shielding effect describes how the interior electrons, so the inside electron orbitals, shield or protect the electrons in the highest occupied energy level from the attraction of protons in the nucleus. And you can kind of see in this image that there's these layers, right, of the electron clouds. Here's the 1s really close to the nucleus. And then as we move out and we're sort of encompassing these other orbitals and getting bigger and bigger, we're getting farther from the nucleus. And if you're out here in the outsides of this 3p orbital, not only are you far away from the nucleus, there's a bunch of crap in the way between you and the nucleus. So the nucleus can't hang on to you as strongly if you're out here. And there's all these layers in the way. Okay, so more layers is going to make it harder for the nucleus to hold on to the outside electrons. And so if you have fewer layers, right, then there's less interference and the nucleus can hold on tight to its electrons. The first important trend is called atomic radius. So in order to think about what that is, I want us to look at this image and we're going to answer a couple of questions. So what does the light blue represent in the figure at the right? This light blue shows the electron distribution in a molecule. What do the black dots represent? These are the nucleus, right? These are the nucleus of the atom. And what are the two ways to measure atomic radius? If you look at the figure, it shows us a couple things. It shows us the bonding atomic radius, which is half of the distance between the nuclei. And then we have the non-bonding atomic radius, which is just from the nucleus to the very outside of the furthest electron cloud. Go ahead and take a guess. Which way do you think is most commonly used, and why do you think that? So what scientists settled on is that we use the bonding atomic radius, 1/2 d, because it's really rare for us to be studying elements that aren't bonded to anything else, right? The only elements that really hang out and aren't bonded to anything else are the noble gases, and they don't do a lot of chemistry anyway, so whatever. And so the atomic radius is a little more useful to think about for our guys that are bonding, and so we might as well think about what that radius is when they're bonded. The formal definition of atomic radius, therefore, is half the distance between the nuclei of two atoms of the same element bonded together. All right, now let's take a look at what this trend might be on the periodic table. So take a peek at this graph. Notice that the x-axis says atomic number, and it's in increments of 10. And then on the left-hand side, it says calculated atomic radius. And so I want you to try to look at this, look at your periodic table, and make some sense of what is represented by the purple dots, the green dots, the red dots. Once you do that, hopefully you realize that these purple dots are the S block, the green dots are the P block, and the red dots are the transition metals. So we've got like hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, and then up here, this is sodium, and then we go through again, okay? Why do you think there are big jumps in radius between the end of a green set and the beginning of a set of purple dots? Why do you think the atoms get bigger? So the atoms get bigger because you add a principal energy level. When you go from a p orbital, right, you're done p6, now you're adding another energy level. When you're adding, in this case, you'd be adding 3s1. And so you got bigger because you added an entire new energy level, and we know that the energy levels represent how far you are from the nucleus. So if you get a higher energy level, you're going to be farther from the nucleus. What is the trend across a period? So if we think about what that looks like, across a period would be from the top purple dot to the bottom green dot. And we can see that across each period, even our transition metals, right, we get smaller and smaller and smaller. Now we can look at the trend down the families. So that would be looking at like each of the top purple dots, what do they do? Each of the second purple dot, what do they do? What does the bottom green dot do? And we can see that as we go down a family, the radius gets a little bit bigger and a little bit bigger and a little bit bigger and a little bit bigger. So the radius of something at the top of the table is going to be smaller than the radius of an element in its same family at the bottom of the table. Why do you think atomic radius decreases across a period? Please ignore my typo. I promise I can speak English. So why does this happen? This goes like this because you're in the same energy level, right? So you're the same distance from the nucleus, but every dot, we're adding a proton to the nucleus. So you're the same distance away, and you have the same shielding, but your magnet attracting the electrons gets stronger and stronger. So you add another little magnet, and it can pull the electrons in tighter. You add another magnet, it can pull the electrons in even tighter, and so on and so forth. That's why we see that theme throughout all of our periods. So the atomic radius decreases across the period because the number of protons in the nucleus increases, attracting the electron cloud to the nucleus and decreasing its size. And by its, I mean the atom's size. I should have been more explicit. Sorry about that. So now let's use that logic to talk about a family. So why does atomic radius increase down a family? Atomic radius is going to increase on the family because, like we were talking about, you add an energy level every time you go down a row on the table. And so every time you add an energy level, you get farther and farther away from the nucleus, and so it's going to get bigger and bigger. On your periodic table that is now beautifully colored and labeled, go ahead and add this trend. Decreasing atomic radius from left to right, increasing atomic radius from top to bottom. All right, next trend that we care about is first ionization energy. And first ionization energy is the energy required to remove the easiest electron from an atom. And so what we mean is if you are trying to attract an electron away, which one is going to give up first? Which one is the most vulnerable to be snatched up? So here is our representation of that. This blue group, we haven't really seen blue before on the graph, but this blue group to the far right, those are the lanthanides. So purple is still group 1 and 2, so the S block, green is still the P block, D is still the red block, and now we have the lanthanides in there hanging out as well. All right, so trend across the period. The trend across the period is that we have mostly increasing ionization energy. So we're like, all right, got harder to take an electron, then it got a little bit easier, then it got harder again, then it got a little bit easier, then it got harder to take an electron again. But the overall theme, right, is that it's increasing. Even though there's some little hiccups in the middle of the period, it's increasing. Across or down a family, if we look with the purple guys, right? So here's this family, and holy Moses, that's really hard to take that one, but then it's not too bad to take these guys. So if we look down their family, it gets a little bit easier, actually, right? So we can look at these top green dots as well. It gets a little bit easier as you go down the family. It gets easier to take away an electron. So that's kind of interesting. Why is this trend a thing? So your magnet, as you go down or across the period, is getting stronger and stronger. If your magnet's getting stronger, it's harder to take away that electron. That's all, right? First, ionization energy increases across a period because the number of protons in the nucleus increases, attracting the electrons to the nucleus with more strength. Now let's talk about the family. It decreases down the family because we have more shielding, right? So we have more layers in the way. It's harder for the nucleus to stay strong and hold on to its electrons. And as you go down the family, it gets more protons too, right? So its magnet is getting stronger, but the shielding is more powerful than the magnet getting stronger. So even though the magnet is stronger, the shielding totally cancels it out and then some. Okay, so ionization energy decreases down a family because there is more shielding in larger atoms, decreasing the attraction of the nucleus and making it easier to take an electron. We are going to get into some gritty detail about this whole ionization energy situation probably on Wednesday. It's going to kind of just depend. I don't know what my immediate future holds right now. But yeah, we're going to get into that, and we're going to talk about why there's some little hiccups and all those interesting, delicious things. Okay, here's your trend. Increasing ionization energy from left to right, decreasing ionization energy from top to bottom. Last but not least, electronegativity is maybe the most important one to understand out of all of these. Electronegativity is the ability of an atom to attract electrons when the atom is in a compound. So electronegativity says that, okay, I'm going to bond with you and I'm going to share your electrons unequally. Like I'm going to take most of the electrons, even though we're supposed to be sharing. And so electronegativity is a big deal because it really tells us a lot about how things bond and why they do what they do. So take a look at this graph. This one looks wild, especially compared to the ones we've looked at before. And let's think about the trend across the period. So across the period, we can see electronegativity just goes up, 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 up. Trend down the family, it goes down, down a little more, down a little more. And it kind of zigzags a little bit. So the trend for families in electronegativity is not as strong as the trend for the period. But the little bit of a downward trend in electronegativity as we go down the table is still interesting and important for us to know. So let's think about why this happens. Why does it increase across a period? Same reason everything else has been happening, right? More protons in the nucleus, stronger magnet. Boom. So electronegativity increases across a period because the number of protons in the nucleus increase, attracting electrons to the nucleus with more strength.